Good evening, everyone. Welcome back to NPTEL's live session, which is for week 12. So today is officially our last lecture, and there will be an extra session on 19th this week. And in that extra session, we will be covering whatever we have studied so far. If you have any doubt, any query regarding any assignments, so you can come up with your questions. So that would be a light start. We'll wait for a few others to join, then we can start the session. Thank you. So, as last sessions also, we were explaining some examples of iron-based systems. where we are talking about the influence of pollinational environment, effect of weak and strong ligands, instead audible splitting, electric field gradient, isomeric shift value. So we have taken a lot of examples actually, where in different scenarios we have tested like how iron in different oxidation states it is going to give you different patterns of in isomeric shift particle stripping. So in this last session, we will be talking about the mixed valence complexes, which is the last topic. So now it's for spectroscopy of mixed valence iron complexes. This we have already initiated in the last class, but that was just a brief intro of it. Okay. So this is classified into three types. First one is the class 1, which is your localized ions, which means that if iron 2 and iron 3 are existing, they will exist as a localized pair. No further change will happen, and hence in the Mossbauer spectra, these both are distinguishable. Right? So say I am expecting that my Fe3 peaks are going to be here, and similarly the Fe2 peaks are going to be here. This is Fe2, this is Fe3. So these both are distinguishable, right? So these come into category of localized iron. Such complexes where both the iron centers in two different oxidation states, they are localized, they are not going to have any exchange of electron any further, and therefore they are distinguishable. Coming to the next slide, the next class is class 2, which is delocalized ones, but distinguishable. Which means iron 2, iron 3, as we are saying, they are delocalizing. So that exchange would happen. 2 will go to iron 3 by giving one electron, and 3 will take one electron, reducing itself to iron 2. So this have been delocalized, but still we started with Fe2, Fe3, we ended up with Fe3, Fe2. So Fe2 slash Fe3 pair is still they are still distinguishable because they are maintaining two different states, right? And the last type is class 3, which is a delocalized ions and indistinguishable, which says if we have iron 2, iron 3, it goes to iron 3, iron 2, but appear as iron 2.5. So this is the observed state, and therefore both are indistinguishable. This is clear that in first scenario we saw that no exchange is going to happen, and therefore they are localized and distinguishable. Second, even if the exchange is happening, still they are distinguishable. And third is they are delocalizing. That means there is an exchange of electron, but both of them they appear as iron 2.5, an average of the both, and hence becomes the indistinguishable. I hope this is clear. Okay. Next, we move on to an interesting example which behave differently in different solvents. Effect of coordinating solvent into here. Example 1. So here we are having 3 iron which are bridged by an oxygen bond. Besides that, there are acetates also. Two acetates bridging with 2 iron centers. Similarly here, here as well. Right? And these iron centers, they are connected with iridium moieties. Similarly this side. So I've made with a different color so that it is easy to define like which binding we are talking about. So here if you see, we have this acetic acid which stays, since this is a weak acid, it stays as in equilibrium with acetate plus release of the proton. And this acetate acts as a bidentate. Bidentate means the two coordination with two atoms, right, of that ligand. So this is a bidental ligand which is bridging between the two iron centers. Now let's talk about the total charge distribution. So if we count that there are six acetates plus one oxo. One acetate gives one minus, one oxo will give you minus two, total is minus, right? And we have three iron centers, and if we have to distribute that into minus 8, it would come across 2 iron 3 and 1 iron 2. So that it would become 6 and this would become 2 positive. It would give you, if you go with other way down, if you take 2 of iron, that will become 4 positive, and 1 iron 3, that will become 7. So only this particular combination is going to hold true for your total balance of the plus, right? And these are the neutral ligands, where only the lone pair of your pyridine is going to coordinate with the iron metal. Now, there are two solvents that have been used, and in two different solvent mediums, their Mossbauer spectra looks differently. How? So, the question is how the Mossbauer spectrum appears differently in different solvents, right? The first case that we have is with the benzene. The benzene as the solvent. Second is your methyl chloroform, CH3, CCl3, right? Now in first case, the spectra that comes across is having iron 3, because we said that iron 3 is there. So iron 3, it is expected to have more delta value, less delta value. Then again at the same position, three different temperatures it is, followed by similarly, we also see iron 2 here. So you can consider it as a 2:1 ratio here due to the limiting of space I can make it, right? So this is the temperature 298, which is room temperature. Here it's 240 Kelvin. Then we are decreasing the temperature, and we see localized iron 2, iron 3 at all temperatures, right? This is the case of benzene. Now let's take the case of when we have changed the solvent to a substituted chloroform. So firstly, we only saw one at 298 Kelvin, followed by at 240. Then we have, and next is 120 and 80. So the different color. At 240 we saw expect like peak has started forming at the same place. Now 120 it started distinguishing, small peak started coming, and 80 May it was clearly visible, right? So it is seen that at higher temperatures it is delocalized and indistinguishable. Now the reason. In benzene, we saw that at all temperatures, two localized signals for iron 2 and iron 3 were there, distinguishable. But in methyl chloroform, at high temperatures, it behaves as iron 2 and 3 are delocalized and indistinguishable, whereas at low temperature, they become localized. Like movement has been frozen, right? So the reason is uh, in CHCl3, CCl3, it is an isolated molecule. Isolated means that there is no interaction between one molecule to other, and because of the random motion, so they become kind of delocalized, and iron 2.5 is observed. Whereas in benzene, in lattice formation, benzene we know that it is having a pi electron cloud, so that stacks with the pyridine of the molecules that hold more complex because of the intermolecular that stacking forces are there. So intermolecular interactions. So these intermolecular interactions make the molecules less dynamic. That is, their movement is now restricted. So once the movement is restricted, iron centers cannot move, and therefore they are called localized and hence distinguishable. Whereas in case of CH3Cl, CCl3, when you are lowering the temperature, that is, when you are lowering the temperature, it is making very clear that lowering of the temperature, it is reducing the dynamics of your molecule. You are freezing your molecule, and when freezing of your molecule is happening, that would lead to localization of your iron centers, and hence it would give you a proper, it would give you a proper separation or distinguishable separation of the both the things. I hope this is clear. Please let me know if you have any doubts so far. If not, then we move to our example 2. So here we have a structure which is bound with nitrogens and sulfur, enriched with sulfur, and here is a cobalt center also. Iron, nitrogen, nitrogen, nitrogen. These nitrogens are connected with each other this way. Right? Okay. So here, what would be the valency of this particular system? So what we saw here, let's see the spectrum first. Okay. So firstly, at 353 Kelvin, we saw at 353 Kelvin, we saw a peak called Rn 2.5. Then started decreasing tendency. At this point was very less. Ultimately, then it was not there. Then we started having there one more peak, which is of RNC. That started increasing. And the female value. Also, we saw one more doublet here. So this is your Rn2 plus. Right? So Rn2 plus is having more positive delta value followed by 2.5 and then C. That's very clear. That's why the picture is looking like that way. So this appears at 298 Kelvin followed by 80 Kelvin and then 5 Kelvin. So what we started with is the 2.5 centers, localized ones, and we ultimately reach to the delocalized ones. So this is how from the spectra we get to know about the exchange of the two centers, whether they belong to class 1, class 2 or class 3. Let's first understand. So because of the sulfur bounded over here, this is getting charged because of the cobalt and therefore it makes the iron centers as the low spin centers. So if you are saying one is Rn3, other is Rn2, so Rn3 low spin if we have to draw, we are since it's an octahedral state, you can consider it iron low spin is D5, iron 3, 2 is low spin D6. This is your energy. This is Eg and this is T2G. It would be totally paired. So we can give a reason over here that because sulfur bound to cobalt becomes highly charged, like metal to ligand transfer, therefore makes iron as low spin. Now, in the first case, in case 1, we have valence contribution, which is not zero. Okay. We have lattice contribution because half of the molecule is nitrogen bounded and half is sulfur bounded, two different types of ligands. So it is also there because two different types of ligands are connected. and here unsymmetrical filling of the electron. So it would give you a large EFG. That's why you can see the RNC is having large EFG, very huge splitting. Whereas in case of this, the other one, second valence contribution is zero because it is a symmetrical filling of the electron. Lattice contribution is there, as you can see. So a decent EFG would be there, right? Now, how the interaction works in these cases, why on heating we are seeing the exchange and on lowering of the temperature it is not there. Only, so firstly we make the orbitals of iron, sulfur, cobalt, sulfur and iron. Orbitals. Cobalt and iron are having V orbitals, sulfur is having P orbitals. So okay. Okay. So firstly, here are the two electrons. If this iron is in plus two, it will give the electron to so here we have two electrons from the iron. It would transfer the electron to here. That would be transferred to cobalt since this is vacant. And then once this is here, it becomes a charged one. And that gives an electron to iron. So this iron, this is a cobalt 3 low spin. So Eg is totally vacant. So they are taking electron from here, making it iron 3 and making this one iron 3, right? So the transfer is happening on heating, only, interaction happens and exchange happens. That is why here you have seen when we are going from higher temperature when the exchange is happening, so they ultimately goes from plus 3 to plus 2 and exist as 2.5. They become delocalized and indistinguishable. Whereas when we are lowering the temperature, one is iron 3, one is iron 2, right? So going from one electron to other, so one electron goes, it goes from 3 to 2.5, and this was already 2, it is taking one electron, it is going from 2 to 2.5. Okay. So I hope this concept is also clear. Now we go to our next example. Example 3 is here. iron sulfur clusters. So we have also taken a lot of examples with iron clusters, but this is little different. So here we are taking first as 2 iron, 2 sulfur peridoxal. These are electron transport proteins, and the structure is they are bound with sulfur and having another coordination with amino acid S16. So when they are localized, their oxidized form would be iron 3 and iron 3. In reduced form, one center is iron 3 and other is iron 2 because one electron has been formed. So iron 3 would give you this value of isomeric shift and 0.6 of quadruple splitting, whereas here the iron 3 is 0.35, 0.657 of iron 2, 0.6 of this one, and 2.7. Expected because iron 3 is 35 since it's a tetrahedral system, it is always high strength. And iron 2 is so more EFGs there in iron 2 system. It is expected. Moving to the spectrum. So firstly we get this one. So this is 1:1. This one is your iron 2 and this one is your iron 3. Iron 2 is having more EFG, that's why it is drawn to that side. This is your iron and they are existing as same in this one. If we change two of the, so now in peridoxin, if two S16 moieties are replaced by two N-histidine, then how the spectra will look like? That would called, it will be called as rescue protein in rescue protein, the oxidized form, which is your iron 3, the delta values are 0.24, 0.32, delta EQ is 0.62, 0.91. Why they are different? This is for the FeS4 system here, and this is for the FeS2N2 system. What I said is we have iron here, this is sulfur, here it is bound with 16, 15, and here it is bound with N-histidine and N-histidine, right? So this center, which I'm highlighting with yellow, mm, so this center which we have here, this is the iron S4 system, and this center is your iron S2N2 based on the coordination. So that's why the values they change when your coordination is also changing, followed by when we have a reduced form. May we have iron 3 and iron 2, again delta, delta EQ, this is 0.31, 0.63, this is 0.74, 3.01. Actually, it is 3.05 for iron S4 system and iron S2N2 system. So you can see how much difference it has given when we go from when the two substitutions have been changed. Earlier, what was the scenario? Here, now, right? So how the difference in the ligand environment or your environment around your metal center is going to change and affect the delta and delta EQ value. Now we have the last example. For every four sulfur cluster. Earlier we have uh, 4Fe3 sulfurs, so 3Fe4 sulfurs. Now again we will make a cube. Okay, okay. So there are two possibilities. First one is the when this system is having a redox potential of minus 4152 minus 280 versus standard hydrogen reactor, right? So in the oxidized form, it exists as 3, 2R3, 2R2, and in reduced form, it exists as 1, 3, and 3, 2, right? So here, if you'll see, if we have uh, 3, 2, 3 and 2, 2, what we are going to have it. So this is total 10 positive coming from Rn3 and this one. If we have 4 S2 negative and 4 S16, S2 negative would give you -8 and this would give you -4. This is total -2 charge, right? So in that scenario, and when we are reducing it also, in the reduced state also, it would be +9 -8 -2, that is -3, right? So in this particular case, in this scenario, we are having a total net of iron 4, S4, either -2 charge or -3 charge, and more negative. Therefore, your delta G is positive. So this system, when delta G is coming to be positive, it's a non-favorable system because the energy demand is so high. So this is not favorable. Whereas we have second possibility of high potential iron sulfur 14. So their potential ranges +90 to +460 millivolt versus SHE. They're also called as with this short form. So here the oxidized form would be P, 3 irons between +3 and 1 would be +2, and used would be 2 in +3 and 2 would be +2. And here if you'll see the net charge, it would give you Fe4S4 net charge of -1, and here the net charge is of -2, which is, so this is more favorable, right? So it's kind of more favorable. Now let's see their pattern. So in the first scenario, the case first that we have seen, in oxidized state it was P2, 3 and 2, 2. So theoretically, it should be, so theoretically expected, it should be 1:1, iron 3 plus 2. But experimentally, what we see is iron 2.5, an indistinguishable one, with the delta value of 0.42 and 1.12 millimeter per second. So what we are actually saying, so we only see for iron 2.5 and no signal for Fe2 positive or Fe3 positive, right? In the reduced state, it is expected 1, 3 and 3, 2. That means 1:3 ratio is expected, but what it comes is experimental. This is expected. So what actually comes is, it comes as a 1:1 ratio. 1:1 ratio appears. Why? Because here what happens, these centers become Rn 2.5, Rn 2.5, and the other are Rn 2 plus, Rn 2 plus. So that's why it becomes 1:1. In the case 2, which we called as HIPFB, here also the oxidized state, we have three, three, three iron centers in Rn3, so it is expected to be 3:1. But the two centers, they go to 2.5, 2.5, 3 and 3. So this is 1:1 ratio. This is experimentally observed. Alright, and the delta value is 0.29, 0.88 for Rn 2, 3 and Rn 2.5, and delta EQ is 0.40 and 1.03. This is for Rn 3, this is for Rn 2.5. And for the reduced state, so it would be Rn 3, 3, 2, and 2. So the count like it would give only 0.5. So this is exactly same as that of the oxidation state of 4 iron, 4 sulfur, first case, as case first. Right? So this is how we get to know about the different possibilities, different environments, how the ligand substitutions and in different solvent mediums, how it is going to change and need preference. So if there is any question, please let me know. So here are some assignments because it was more of 2 or 3 samples which have been left. So just need to revise the concepts. So the first question that is to record Mossbauer spectrum of iron containing samples is source X is used. X after new transformation to Y is gamma radiation, which is used in Mossbauer spectroscopy. X and Y respectively. So we know that since the iron 57 is required, we need iron 57, which is naturally not abundant. So we take the abundant source, which is 57 cobalt. So this is our source. And after electron capture, it converts to 57 iron. So the option 3 is the right option. Okay. Among the following, those can act as Mossbauer nuclide. We already know that iron is the one, iron is the one, and antimony is the one. Only A and B. Cobalt is not Mossbauer active nuclide. So, option C. So these are some examples that we have already taken earlier. You can just practice. So this is your homework. You can try by yourself, and if there is any problem, please let me know. So this is from your earlier slides also. You can just try by yourself, or if you want to try it now, you can try it and I'll be telling you the answer. Besides this, if there is any doubt or question, please let me know.